enzymes, and we've looked at the processes. We've named the common names for processes transitioning from solids, liquids, and gases, and we're going to study them a little bit more in depth today. But we're more so going to talk about the kinds of forces that are occurring between molecules to hold them in that state of matter. Okay, so the intermolecular forces are what we're going to call them, which are forces that are occurring between molecules. Okay, not within a molecule, but between neighboring molecules. Okay, so we're going to zoom in first on this picture on the left here, and you can probably already guess and label. Go ahead and label gas, liquid, and solid on these three spheres. And we're just going to start with the picture on the very far left, A. A is what? Gas, liquid, or solid, based on what you know about it. Gas. Okay. Thank you, Ashlyn. It is a gas. How do we know it's a gas? We're going to really look at two things about these states of matter that we're going to analyze between gas, liquids, and solids. And one is the amount of energy within the molecule or in the molecule. So what do you know about gas particles? Do they have lots of energy or very little energy? I mean, the picture kind of shows
lots of energy.
Yeah, they have lots of energy. Okay, so we're going to write high. I'm going to abbreviate KE, kinetic energy, high amounts of kinetic energy. That's right, lots of energy. They're moving. I like to think of, and the particles here being the red spheres in this picture, I like to think of it as cars on an interstate. They're zooming past one another, and like cars on an interstate, do you have time to chat to the car next to you on the interstate? No, okay. There's not a lot of interactions at play between gas particles, whether it be an atom or a molecule. There are no, we're going to call them intermolecular interactions. No intermolecular interactions, okay? They're not interacting. They're free to act independently, each particle. And then they have high amounts of energy. So I'm going to shrink this down a touch. That's gases, all right? So the middle picture is what? Liquids or solids? Ashlyn says liquid. Dakota says liquid. That's correct. You can see some space between these molecules, the red spheres. So they're kind of fluid, but there's not as much space as the gas particles. So they're closer together, but they can still move. So this is definitely the liquid, which means this one's the solid. All right. So these have less kinetic energy. And what would you say about, they still have some though, they're still moving. So they have some kinetic energy. What would you say about the interactions between these particles? You think they have some interactions, no interactions, lots of interactions? Some. Dakota says some. I agree. It's kind of not as much as gases, or sorry, more interactions than gases, but not as much as solids. So we'll say some intermolecular interactions. All right, some intermolecular interactions. And then lastly, solids. If you look at this, the molecules are all touching one another. They're very ordered and arranged. We know solids have the least amount of disorder. They are the most ordered. Gases are the most disordered. So they have very little kinetic energy, and they have strong intermolecular interactions. Okay. So those are the two things, two qualities here that I want us to understand as we move between solids, liquids, and gases, how the amounts of energy, which, you know, we can also communicate the word energy by using the word heat. Heat and energy are synonymous words here. So the more we heat up molecules, the more energy they have, the more gas-like we become. The more we take energy away or cool down molecules, take away heat, the more solid-like they become. So as we go, we can actually kind of write that as we go from gases to solids, We are losing kinetic energy, and we are increasing or strengthening, you could say either word here, increasing the strength, we'll put it that way, of intermolecular interactions. Okay. So we've been talking about bonds within atoms of a molecule, like ionic bonds, covalent bonds. Now we're going to talk about bonds per se. They're more so just interactions between neighboring molecules instead of within a molecule. All right. So that's this side of the slide. I'm going to slide over to this figure over here on the right side. I'm going to zoom in on it. This is essentially showing you the common names for transitions between solids, liquids, and gases. And you probably recognize most of these names, okay? Melting obviously takes you from a solid to a liquid. Vaporization, condensation, freezing. But what I want to point out is you can see in parentheses these little phrases associated with each change, and it's telling you whether heat was absorbed or heat was released. Okay, so if gases have high energy and solids have little energy, okay, then it makes sense as you go from a solid towards a gas, okay, so I'm going to kind of trace over these arrows because that corresponds to the red. It makes sense that you're absorbing heat. You're increasing in energy, okay? To melt ice, you have to absorb heat. To vaporize or boil a liquid, you have to take in heat, okay? Vice versa, the statements in blue correspond to these arrows that I'm going to trace over in blue. As you condensate something, going from a gas back to a liquid, you have to release heat. And then same for freezing. Now, if we had to go in, well, let me address these two changes over here first. If you're going, you can also go straight from a solid to a gas and vice versa. So going straight from a gas to a solid, that's like past condensation, right? It's skipping the liquid state. We call that deposition. You're releasing a ton of heat. And then you might be familiar with this word, sublimation. Can anybody think of an example of a substance that sublimates, goes straight from a solid to a gas? It doesn't melt. There's one substance, it's kind of common. Once I say it, you're probably familiar with it.
Is that gas? Like gasoline?
Gasoline, like what you'd pump into your vehicle. That's a liquid. I don't know. I'm thinking of dry ice. Has anybody heard of dry ice? Yeah, thank you, Tiara. Dry ice. So dry ice does not melt, okay? It goes straight from a solid, ice, to vapor, all right? Does not melt. So that's an example of sublimation, all right? Now, if we had to go in here and assign a delta H and a delta S, could you do that? I want you to think about these processes, okay? If we are absorbing heat overall, is that an endothermic or an exothermic reaction? If you're absorbing heat overall, is that endothermic or exothermic? Thank you, Zoe. That's endothermic. So for endothermic, what's the sign on delta H? Positive or negative overall? Is your delta H positive or negative? It is positive. So we could go in here for all these heat absorbed processes. We could write in a positive delta H. That process has a positive delta H. This one up here, vaporization. Anything in this direction from solid towards gas has a positive delta H. Anything where you are going from a gas back to a liquid, back to a solid, so and releasing heat, that's exothermic. And if you're exothermic, you have a negative delta H. So we could go in and we could assign, if I gave you a process, you should be able to tell me the sign on delta H or delta S, okay? Vice versa, let's think about delta S. If we are going from a solid towards gas, so melting or vaporizing, what would the sign on delta S be? Is your disorder increasing or decreasing? Would delta S be positive or negative? If you're going from a solid towards a gas, so melting or vaporizing. Janelle says positive. Anybody agree, disagree? What's happening to the amount of disorder Yeah, you're increasing in disorder. So your delta S would be positive for these as well. Okay, and then for the other side, if you are going from a gas back to a solid, which is the most ordered, this is ordered, this is disordered, then your delta S is also negative. So it's kind of nice they match. So keep that in mind. If I gave you a process, could you tell me the sign on delta H or delta S? If you use this figure, hopefully you could. All right, any questions on this slide before we move on to the next one?
I do. I have a question.
Yes.
When I was reading about it in the book, there was a question and it was asking if it was favored or unfavored. And I thought that a positive delta S meant that something was favored. But when I look at the answer in the back of the book, it says something different. So I wasn't sure if I was confusing myself.
Positive delta S favors a negative delta G. So a favorable entropy is a positive delta S. So if you want to screenshot that or something or send it to me, I'm more than happy to look at that for you.
Okay, awesome. Thank you.
Send it to me in the email. Yeah, what's favorable? Okay, and remember a negative delta G is favorable. So what's favorable overall, what's going to give you a negative delta G tends to be a negative delta H and a positive delta S. Okay, positive entropy is favorable, negative change in enthalpy is favorable. Great question. Thank you for that. Okay, moving on. Intermolecular forces. So we're going to talk about three kinds of forces that occur between molecules and kind of hold them together, and how those affect different properties for different states of matter. Properties meaning like boiling points and melting points and things like that. So the first type is called dipole interactions. The second kind we're going to talk about are called London dispersion forces. London dispersion forces. And there's a nickname for these as well. And you'll probably hear me use both, and the book uses both. They're also, I'm going to zoom in really quick. They're also known as van der Waals. Van der Waals forces, London dispersion forces, same thing. Okay, that's the second kind. The last kind we're going to talk about is called hydrogen bonding. All right, and I'll give you a heads up. Hydrogen bonding is the most complex, so we'll probably spend the most amount of time there today. But once we talk about and define these three, we're then going to practice identifying, if we look at a kind of any chemical formula, like water or ammonia or any molecule, how do we know what kind of interactions are going to be at play between identical molecules of that substance, okay? And then how would that affect their boiling point, melting point, vice versa? Okay, dipole interactions. Dipole. So we're going to fill in a few blanks just to define a couple things, and then we'll see how that affects some properties. So dipole interactions, for what kinds of molecules do they occur in? Molecules that are polar and have a dipole. So I'll remind you, how do we draw in a dipole on a molecule? They experience dipole interactions. All of this, by the way, a lot of this of what we're going to do today is going to draw on chapter 4 stuff. Lewis structures. Angelina, do you need me to go back to anything? I got it now. Okay, good. So molecules that are polar and have a dipole, they experience dipole interactions. So you need to make sure that you remember, or remind yourself if you don't, or reach out to me and let me know how to draw a dipole in on a molecule. We'll do some examples of that. Dipoles, for molecules that are polar, they have a permanent dipole, okay? And so we're talking about a dipole that does not go away. It's a permanent, I'm trying to figure out, I'm just going to write in here, permanent dipole. Because in a little bit, we're going to look at what a temporary dipole is. And in a permanent dipole, remember, it's that the positive, or in dipole-dipole interactions, what happens is the positive pole of one molecule, and the positive pole is the one that's the semi-positive, kind of the little squiggle positive, the delta S, is attracted to the negative pole of another, okay? And they are stronger than London dispersion forces, but they are weaker than hydrogen bonding. So they're kind of the middleman when it comes to strength of intermolecular forces. They're stronger than London dispersion forces, but they are weaker than hydrogen bonding. So let's look at some examples. When you have molecules that are polar and they have a permanent dipole, remember dipoles, we draw in like that, and we draw the arrow pointing to the semi-negative side, and the little cross on the arrow corresponds to the semi-positive side of the molecule. So look at these ovals over here. These ovals represent a molecule with a permanent dipole. We could draw it in for every molecule if we wanted to. What will happen when you have molecules that are polar? They'll align themselves. The positive region of one end is going to be close to the negative regions of surrounding or neighboring molecules, okay? And that's what they're trying to show you with the red and blue here. Now, here's the deal. One little dipole-dipole interaction between two molecules may not be a big deal. But usually for substances, especially like in the labs and stuff, we're working with milliliters or liters or grams of stuff. And that's like millions of molecules. So if you had a whole sea of these molecules, and you imagine, millions and millions of these little ovals lined up next to each other, the dipole interactions do add up. Those forces do add up, and it does affect properties overall on a large scale. Okay, here's an example of how this can happen. I want to look at these two molecules here. We have butane, C4H10, and we have acetone, C3H6O. So they have very similar numbers of carbons and hydrogens. Well, not necessarily hydrogens, but what is exactly identical on these two, look at their molecular weight, mole weight. This is 58 AMUs. For one molecule, that's how much they weigh. They both weigh the same here. So essentially what I'm trying to say is that the size of these molecules is pretty identical. But right underneath that, where it says BP, this stands for the boiling point of these molecules. And look at that. One is negative 0.5 degrees Celsius. So for butane, it's negative 0.5 degrees Celsius. And for acetone, it is 56.2 degrees Celsius. Now, what's the difference between these molecules? Let's talk about butane. Is butane polar or non-polar? What do y'all think? Is butane polar or non-polar? It's only got carbon and hydrogen in it. So the questions to ask yourself here is a carbon-carbon bond, okay? The bonds between the dark spheres would be these are probably your carbons, and then the bonds between the smaller spheres, these are your hydrogens. Is a carbon-hydrogen bond or a carbon-carbon bond a polar bond? Now, I know you don't have your electronegativity chart sitting, some of you may have it close by, but we don't have it right here. We will have it a few slides down, and I'll put that on the resources page for you for exam 3. What do y'all think? Carbon-carbon bonds are non-polar, right? Because they're between identical atoms. So there's zero difference of electronegativity. Remember, to calculate whether a bond is polar or not, you have to calculate the electronegativity difference. And if you have two identical atoms, then the difference is 0. And the carbon-hydrogen bond, when you actually do go calculate it, it's a difference of 0.4. And this is not polar. So this molecule has no polar bonds in it. So it is a non-polar molecule. All right. So it's non-polar, and it cannot, therefore, it does not have dipole interactions. Okay. Dipole interactions, remember, they only occur in molecules that are polar. So let's look at acetone now. Anybody ever dealt with like fingernail polish remover? That's essentially acetone. Okay. Look at this molecule of acetone. What do you notice? We have drawn in on the oxygen-carbon bond a semi-negative and a partial positive. So that is a polar bond. The oxygen-carbon bond is a polar bond. And you see that here with the coloration difference, okay? on the molecule. So because this is polar, this kind of molecule can have dipole interactions, okay? So this one can have dipole. This one cannot. And because of that, so acetone molecules could line themselves up just like what we're seeing up here, with the positive region interacting with the negative region on a neighboring molecule. And it's a difference in their boiling points. That difference alone accounts for this difference of 50 degrees Celsius, over 50 degrees Celsius. And I don't know if you know much about the Celsius scale. 21 degrees Celsius is room temperature, roughly. So a negative 0.5 is like really cold, honestly. So butane is gas at room temperature, and it doesn't take much heat or energy at all to boil it because there's not very strong interactions holding those molecules together. Acetone takes a lot of heat. 56.2 degrees Celsius is very hot. So it takes a lot of heat and a lot of energy because those molecules have an extra layer of attraction and force holding them together. And so we have to heat it up more to break those interactions apart and vaporize those molecules, okay? Questions here with dipole before we move on? Okay, van der Waals forces. Let's talk about those. They occur in all molecules. Every single molecule, even polar molecules, have van der Waals forces. It's just that in a polar molecule, the dominant force at play is your dipole forces. So van der Waals or London dispersion occur in all molecules, but they are the strongest intermolecular force in nonpolar molecules, okay? Because nonpolar molecules can't interact with dipole-dipole interactions, but they can interact with van der Waals or London dispersion, okay? These are the weakest intermolecular force. And what creates a London dispersion interaction or van der Waals force? They occur by interactions between what we call momentary or temporary is another word for this. Momentary or temporary dipoles. What the heck is a temporary dipole? Let's look at that. I'm gonna draw this out. So let's say we have two hydrogen atoms, okay, that are interacting. Hydrogen bonded to hydrogen. Let's just represent those. We know we have the nucleus, and you have your electron cloud, okay? And we know that there are electrons that we represent. This bond is 2 electrons. And the bond here as drawn, that little dash, it makes it look like those electrons are just sitting nicely between the atoms, right? As though they're just sitting right here, all nice and still. But the truth is, electrons are not still, right? Probably about as still as my 2-year-old. Okay, they don't sit still, they're always moving. So we cannot pretend that they're sitting there like that. Electrons are actually all over the place, okay? All the time. They're just back and forth, back and forth, back and forth. So if we took a snapshot at any one given moment, it could be that the electrons, I'm just going to draw them as little red spheres. The electrons could be over here for 1 second. And then what if on a neighboring molecule, well, and if they were, so here's our electrons for the hydrogen atoms, and this would be 2 electrons. What that would create is an imbalance. And this side of the molecule, we could say for that split moment in time, we have a partial negative side and a partial positive side. And if you have another molecule neighboring, so what if can we copy and paste this? I'll see what it pastes. Okay, we're just going to pretend this is the next door neighbor. With the same thing, maybe electrons are over here somewhere. Then what we have is, again, a semi-positive and a semi-negative. And it's this interaction that creates the positive. There's an attraction there between the negative and the positive. And it's just for a split moment, okay? That's why it's called a momentary dipole. So it's different from a permanent dipole because it goes away very quickly. So this seems like it wouldn't even account for anything because it's so momentary, but they do. They do add up across, again, millions and millions of molecules. And this is just a hydrogen atom. So this is just an example with 2 electrons. Let's think about atoms that have 50, 60, 70 electrons. And that's actually the next point with this bullet point, is that large atoms that have 100 electrons, okay, they're gonna have more electrons, and therefore they're gonna have more fluctuation. more movement, right? And therefore they're going to be able to experience stronger or more London dispersion forces, okay? And then molecules also with a larger surface area will have more London dispersion interactions, okay? So how does surface area account for this? Let's look at, I'm going to slide this over a little bit. Let's look at these two molecules right here. We've got pentane and we've got 2,2-dimethylpropane. And don't worry, you don't have to know the name on that. But I want to illustrate a point. These two molecules have the same number of carbons and hydrogens. So essentially, they're almost the same molecule, but they're just arranged differently. You can see with pentane that the structure is more elongated because the carbons are all one after another in one straight chain. Okay, so this one has more surface area. And over here, the Lewis structure is different. The carbons are connected differently. They're not all in one straight chain. And so when you look at kind of the spherical model, this one looks a little more balled up. This one has less surface area. Well, let's see how that affects their boiling points. So by the way, if molecules with larger surface area can have more London dispersion interactions, that means those molecules are held together with more forces. That means it's going to take more energy to break them apart and melt them or boil them. So their boiling point would be higher. So it makes sense. Look, for pentane, the boiling point is 36 degrees Celsius, but for a molecule with the same kinds and numbers of atoms, just arranged differently, the boiling point for this other molecule with less surface area and therefore less interactions, less London dispersion, has a boiling point of only 9.5 degrees Celsius. Okay, that's almost 20 degrees Celsius, which is not insignificant. So if I gave you two molecules and I said, which one has more surface area, which one has less surface area, which one would have a higher boiling point or higher melting point, which one would have a lower melting point or boiling point, you could look at that and then answer a question like this from looking at these reasonings. Any questions on van der Waals forces before we move on to hydrogen bonding? Okay. This picture up here, by the way, I didn't address it. This would definitely be a nonpolar molecule up here. So there's no interactions between the two of those. But these down here, they look like they have a dipole. So this would be an example of polar molecules. So these look like they'd have dipole interactions, and the top would have just van der Waals. Okay, hydrogen bonding. We owe Oh, Hannah, if you got to go, it's okay. You can watch the recording if you can't pay attention. But if you keep your screen muted, then we can't hear you. Sorry, I was reading the chat, everyone. Okay, hydrogen bonding. We owe our deepest respects to hydrogen bonding, and here's why. Hydrogen bond is the king of all intermolecular forces. Look at this next statement. Basically responsible for life on Earth. Why? Hydrogen bonding is actually the reason that we have liquid water at livable temperatures. Okay, water molecules experience large amounts of hydrogen bonding. We'll look at an example in a little bit, but if we did not have the temperatures that we have, if water didn't experience hydrogen bonding, we would have gas phase water on Earth, and we would not be able to have liquid water. And liquid water is important, right? I met somebody one time. They were like, "Oh, I don't ever drink water. I just drink juice and Cokes, and that's what I drink." I was like, "When was the last time you had water?" They're like, "I don't know, probably weeks." And I was like, "You are gonna die soon if you don't drink water, okay?" How much water? We need water every day, right? Anybody know how much water we need every single day? I'm gonna take a drink of water right now. How much water should you drink a day? Anybody know? Come on, you health professionals should know how much water you need to drink every single day. Nobody. 8 ounces a day? That's it? 8 cups a day is better, but how many ounces are in a cup? Anybody know? Yes, 8 glasses, half your body weight. 11 cups for women Let's up that. Okay. A cup is 8 ounces. So you guys need like 64 ounces of water every day. Okay. Are you getting there? Are you dehydrated? Do you feel thirsty right now? Okay. So let's look at DNA. Let's look at some biological molecules. Okay. Biological molecules, many of them are held together by hydrogen bonding. So this is obviously the structure for DNA, and you can see the helix here. I want to zoom in on it. Yeah, I know it's covered up with all different kinds of atoms, but what I want to point out are these red dotted lines, these red dashes. Notice that they're connecting oxygens and hydrogens. Okay. Or sometimes they might be connecting a nitrogen and a hydrogen, but mostly looks like they're connecting oxygens and hydrogens. And these are hydrogen bonds. So literally the backbone of our DNA is held together by hydrogen bonding. So that's one thing, one reason it's important. These dotted lines are also the hydrogen bonding, you can see. Okay. Proteins. Proteins are another example of why hydrogen bonding is important. Anybody know how many proteins are in your body, roughly? Any guesses? I'm actually interested to see what y'all think. How many proteins are in your body? No guesses? Give me your best guess. 240? I feel like I'm on The Price is Right. No other guesses. You have way more than 240. Way more than 275. You have almost roughly 60,000 proteins. That's more like it, Kenethia. Okay. 60,000 proteins in your body, give or take. And all of these proteins are held together. I'm going to say all, probably most of these proteins, depending on the size, are held together by hydrogen bonding. Proteins are like the workforce of your body. They do all the house chores. So anything that gets done, I'm going to say anything, most things that get done are due to proteins. So if we didn't have hydrogen bonding, we don't have human bodies. Okay. So we owe our deepest respects to hydrogen bonding. So now what the heck is a hydrogen bonding? Well, they're very strong. Okay. They're the strongest, stronger than dipoles, stronger than London dispersion. And here is the definition of a hydrogen bond. And we're going to unpack this. Okay, so just give me a second, but let's define it first. It occurs between the lone pair on an oxygen, nitrogen, or a fluorine atom. And we're very specific here, just oxygen, nitrogen, and fluorine, the lone pair on an oxygen, nitrogen, fluorine. And so there's 2 requirements. That's number 1. And the second one is that you have to have a positively, this is requirement number 2, positively polarized hydrogen that is bonded to another oxygen, nitrogen, or fluorine. So I'm gonna just recap what I just said here. Let me zoom out so you can finish writing. A lone pair on an oxygen, nitrogen, fluorine, and a positively polarized hydrogen that is bonded to another oxygen, nitrogen, fluorine. So requirement number 1 is that you have this, an oxygen with a lone pair in your molecule, a nitrogen with a lone pair, and we know fluorine gets 3 lone pairs. Okay, so you got something like this in your molecule. The second requirement is that you have a hydrogen that is bonded to an oxygen, a hydrogen that is bonded to a nitrogen, or a hydrogen that is bonded to a fluorine. Okay, 2 separate things here. And this is the requirement for any substance that can hydrogen bond to another molecule just like itself, an identical molecule. Why all these hydrogens down here? These, we could draw the little positively polarized sign on them, the semi plus. These are all positively polarized. Why? Because all of these bonds are polar. So if you have a hydrogen in your molecule, that does not mean you can hydrogen bond. It only is hydrogens that are bonded to the oxygen, nitrogen, or fluorine. Okay, so if you have a hydrogen bonded to bromine, nope, that's not the kind of hydrogen we're talking about. Even though this bromine has lone pairs, you have a hydrogen bonded to boron. Nope, that's not. It doesn't have lone pairs actually. That's not the kind of hydrogen we're talking about. Specifically, hydrogens bonded to oxygen, nitrogen, or fluorine. Okay. Here's a look at water molecules. This is kind of the way water molecules arrange themselves when you have like a glass of water. You have water molecules that all these dotted lines. This is a whole network of hydrogen bonding holding these water molecules together. And if we're going to vaporize this cup of water, we literally have to break all these hydrogen bonds before water will become a gas, okay? All right, let's look at 2 examples of hydrogen bonding and discuss them a little further. So this is 2 water molecules. All right, these little gray lobes are the electron clouds on the oxygen. The red spheres are the oxygen, and the white spheres, these are your hydrogens. So you have 2 water molecules, and you can see the dots here. This is your hydrogen bond between the molecules. And this is showing you up here just with the atoms drawn in. So the hydrogen right here that has the black arrow pointing towards it, it's got that partial plus on it. This hydrogen is the one participating in the hydrogen bond. And we actually give a name to this hydrogen. We call it the donor. Okay, we call any hydrogen in the hydrogen bond a donor. It is essentially donating any negative charge from any electrons that it has to the oxygen in the hydrogen bond with it. I'm about to sneeze. Maybe not. Maybe I am, maybe I'm not. Anybody been there? Okay, I'm good. I think I'm good. All right, the oxygen also has a black arrow pointing to it. And you see the lone pairs on this oxygen. The lone pairs are what that arrow is essentially pointing to. The lone pairs are the acceptors. So we have a donor and an acceptor. And I want you to be able to define these because we're going to do a whole lab just on hydrogen bonding. It's a dry lab. That's the one we have coming up next. Okay, so any hydrogen bond we have, and the hydrogen bond is the one, is these dots that are connecting the donor and the acceptor. All right, and we can draw in the partial plus and the partial negative on the donor and on the acceptor. Okay, we could also draw an arrow to this other lone pair, and this could also be a potential acceptor. Okay, we don't see it interacting in the hydrogen bond just yet, but we could have it interacting with another hydrogen on another water molecule. Guess what? This hydrogen over here, this could be a donor. If we had another water molecule, if we drew one in, we could draw another hydrogen bond. All right, and then we could label this as the donor and the lone pair on the oxygen as the acceptor. So I want you to get comfortable with that language, and I definitely want you to be able to label donor and acceptor on hydrogen bonds. Let's look at 2 molecules of ammonia. So that's water. Any questions on example there before we slide over? All right, with ammonia, here's 2 molecules of ammonia, NH3. We're very, very familiar with this molecule. Again, you see the hydrogen bond is this red dotted line connecting the 2. And if we had to label these, here's our positively polarized hydrogen. It's bonded to a nitrogen. That's what makes it polar. And then the lone pair on the nitrogen. So how do we label these? How would we label the lone pair on the nitrogen? Is that the acceptor or the donor?
The acceptor.
That's correct. And then the hydrogen here is a donor. Any of these hydrogens as well could be possible donors. They could equally be involved in hydrogen bonds with other molecules. Okay, neighboring molecules. We're not showing that, but they could be, okay? All right. Now, I want to make a distinction with hydrogen bonding real quick, because you have molecules that can sometimes have both. For example, water and ammonia. Within 1 molecule of water, within 1 molecule of ammonia, you can identify and label both a donor and acceptor. So some molecules, I'm going to write this out. Molecules with both a donor and an acceptor, they can hydrogen bond. I'll say H bond. They can hydrogen bond with themselves. Okay. That's the example we see right up top with those 2 molecules of water or 2 molecules of NH3. Because water, in 1 molecule of water, we can label both a donor and an acceptor. These can both be donors. And up here, these lone pairs can be acceptors. Because water has both, it could hydrogen bond with itself. Same thing, NH3 can also do this. But some molecules may only have one or the other, okay? Molecules with either a donor or an acceptor, okay, meaning they don't have both, not both. Can still H bond, can still hydrogen bond, but not with itself. Okay, let's think of an example molecule. And you could draw a dipole on these as well, right? I'm reading Angelina's comment. Yes, you could draw a dipole in for water. We can draw it pointing towards those lone pairs. That's the negative side. These hydrogens would be the partial positives. You could also draw one in on ammonia, pointing towards the lone pair. So let's think of an example for category number 2 down here. Molecules that have either a donor or an acceptor, they just don't have both. What about what's an example that I'm thinking about? A good example would be for let's do CH3 OH. Actually, that one does have both. We had one down here. Which one of these had just one? Let's do this. I'll just modify this one real quick. Sorry. Let's do this. There we go. What if you have a molecule like this? This molecule has hydrogens in it. It also has an oxygen in it, but it does not have a hydrogen that is directly bonded to an oxygen, nitrogen, or a fluorine. So it has the lone pair on an oxygen, and these could be acceptors. But these hydrogens that are bonded to carbon, they are not positively polarized, okay? A hydrogen bonded to a carbon, that is never a polar bond. These bonds are not polar. So these hydrogens are not positively polarized. And if you don't believe me, I'll be right back. I'm just going to scroll down. Here's our electronegativity chart. Here's hydrogen, 2.1. Here's carbon, 2.5. So 2.5, that was carbon, minus hydrogen, 2.1. That's only a difference of 0.4, and that is not considered polar. To be considered polar, the electronegativity difference has to be 0.5 or greater. Okay? So hydrogens bonded to carbon are not positively polarized hydrogens. However, because you have lone pairs on an oxygen, if, say, a water molecule came along, you could still get a hydrogen bond here, because this hydrogen on the water we know is positively polarized. This is negatively polarized. So you could still get a hydrogen bond with water. It just cannot hydrogen bond with another molecule like itself. Okay? All right. Questions here? So we're kind of done talking through the concept part. Now we're going to put this into practice. So I have a poll question in just a second. But what I want you to do is look at question number 1 here. We're just going to review for a minute. We've covered a lot of material. What characteristic must a compound have to experience the following intermolecular forces? What characteristic must a compound have to experience the following intermolecular forces? So London dispersion forces. Honestly, this first one's kind of a trick question. Are there any requirements? We said all molecules experience London dispersion. So there's no requirements here. All molecules experience these. You just have to be a molecule. All right, no specific requirements there. Dipole forces. To experience dipole forces, what kind of characteristic, what kind of molecule do you have to be? Anybody remember what we said? Polar, polar, polar. Yes, you have to be polar. You have to have a permanent dipole, okay? Positive region and a negative region. Okay, hydrogen bonding, what were the requirements there? What kind of characteristics do you have to hydrogen bond? Well, number one, you have to have a positively polarized hydrogen. So I'm just going to draw the semi-plus H, a positively polarized hydrogen. And number two, you have to have a what? What else do we have to have? Lone pairs on, not just any lone pairs, on an oxygen, and nitrogen, and fluorine, right? Lone pairs on an oxygen, a nitrogen, or fluorine. So not chlorine, not bromine, not sulfur, specifically on an oxygen, nitrogen, or fluorine. All right, we're going to look at A, B, and C really quick. And we're going to draw these out because the next question says, identify the dominant intermolecular force in each of the following substances. Identify the dominant intermolecular force in each of the following substances. So to do this, if I ask you a question like this on the exam, how do you answer this? Well, first you need to draw out the Lewis structure. You need to decide what kind of molecule is this? Is it polar? Is it nonpolar? Does it have the requirements for hydrogen bonding? And you can best do that if you draw the Lewis structure out. So I'm going to zoom in. Let's just draw the Lewis structure for nitrogen. So I'm going to draw two nitrogen atoms. They're connected by a triple bond, and they each have a lone pair. So if you still struggle with Lewis structures, you're going to struggle with this material on chapter 8. So make sure you feel good and confident with Lewis structures. If you do not, reach out to me, let me know. I'll set up a Zoom with you. We'll practice them. Go back. There's practice problems from the textbook I've assigned that will help you practice Lewis structures. But looking at this Lewis structure for nitrogen, is it polar or nonpolar? Ashlyn says nonpolar. Dakota says nonpolar. Janelle says non. That's correct. What's the electronegativity difference between two nitrogen atoms? We're doing 3.0 minus 3.0. That's a difference of 0. That is nonpolar all day long, okay? Anytime you have identical atoms bonded together, that is a nonpolar bond, okay? Because the electronegativity difference is 0. So because this is nonpolar, what is the strongest force? London dispersion, dipole, or hydrogen bonding? London dispersion. Great. Okay. Next, we have HCN. HCN, how do you draw a Lewis structure for HCN? So we have a carbon. Carbon has to have 4 bonds. You have a nitrogen. Nitrogen has to have 3 bonds. Hydrogen can only have 1 bond. So you should get something that looks like this. We know nitrogen has to have a lone pair. So now, do we have any polar bonds here? Well, the carbon-hydrogen bond, remember, these are never polar. This is nonpolar. But a carbon-nitrogen bond, carbon and nitrogen, so we're looking at these values right here. The difference between 2.5 and 3.0. That difference is a difference of 0.5. And that is polar. Okay, a difference, electronegativity difference of 0.5 is polar. So these bonds are polar, which means we could draw in a partial positive and a partial negative. Where would you draw them? You draw the partial negative on the nitrogen. It has the lone pairs. You draw the partial positive on the carbon. And you could even draw in a dipole pointing to those lone pairs. Okay. So what is the strongest? This molecule is polar. What's the strongest type of force it's going to have? Can it hydrogen bond? With itself? It cannot hydrogen bond with itself. Okay, because we don't have both a donor and an acceptor. So the strongest force it would have is dipole. Dipole, dipole. Okay. Next we have CCl4. So I'm going to draw that one over here. CCl4 looks like this. And then you got all the lone pairs on those chlorines. Okay. Now, let's think about a carbon-chlorine bond. By the way, I will give you this electronegativity chart again for the exam on your resources page. Carbon 2.5, chlorine 3.0. So the difference between 2.5 and 3.0 is 0.5. So all these bonds are polar. Every single one of these are polar. Right? This one's polar. But is this molecule polar overall? Does it have a permanent dipole? What do y'all think? Any guesses? Yes. One caveat with stuff that's polar, remember, you got to ask yourself, is there symmetry here? Zoe says no, because they cancel out. And what I think she means, if I erase a little bit and clear our structure back up, let's look at this structure. We have polar bonds, but if we draw dipoles in, we would draw them all pointing towards the chlorines, okay? And what I notice is that there is symmetry in this molecule. Two planes, actually. You could draw one north and south, and you could draw one east and west. All these dipoles, the left and the right dipole, they cancel out. The north and the south dipole, they cancel out. So because they all cancel out overall, this molecule is nonpolar. So the strongest interaction it will experience between two molecules of CCl4 would be London dispersion. Okay, that would be the dominant force between two identical molecules of CCl4. So now I have a poll question. I'm going to launch this. We're closing in on the end of lecture, so this will be the last thing we do. I want you to draw out the Lewis structures for D, E, and F. Okay, I'm going to pull the poll up, and then I want you to identify what's the strongest force between two identical molecules. So 2 molecules of NH3, 2 molecules of CH3Cl, 2 molecules of CH3COOH, and put in your answer for each of those. I'll probably give you, you may not be finished, but we're going to go over all these. I'm going to give you about 30 more seconds because we only have about 4 minutes of class left. I don't want to go over. So I'm going to end the poll in about 20 seconds. So just get as far as you can. All right, we're about 75% voted. I'm gonna go ahead and end it. Even if you haven't voted, it's okay. We're gonna go over these. We'll see what the majority of people said. Okay, here are the results from the polls. So number 1, the dominant intermolecular interaction for NH3, 2 molecules of NH3, they said, most people said hydrogen bonding, but we also had several people pick London dispersion, dipole, dipole. So let's look at this. Let's draw it out. I'm going to come down here. So D was NH3. If you draw this out, you should have a Lewis structure that looks like this. All right. Now you're asking yourself, well, let's just start with hydrogen bonding. Do we have the requirements to meet hydrogen bonding? Do we have a lone pair on a nitrogen, oxygen, or fluorine? Yes, we do. It is right here. Okay, so that's one requirement. Do we have a positively polarized hydrogen? How do we know what is a positively polarized hydrogen? Is a hydrogen that is bonded to an oxygen, a nitrogen, or a fluorine. And we have 3 of those, okay? All 3 hydrogens here are bonded to a nitrogen. And if we look at the electronegativity difference between hydrogen and nitrogen, which is right here, the difference between 2.1 and 3.0 is 0.9. So this means all of these are polar. So we could literally draw in the positively polarized little delta squiggle S on all these hydrogens. So what that means is we have 3 acceptors, sorry, donors. Whoops. And we have 1 acceptor. And because we have both, this molecule can hydrogen bond with another molecule of itself. So the strongest force here would be hydrogen bonding. Okay. Yes, this molecule is polar. So yes, it would also experience dipole interactions. Yes, this is a molecule. So yes, it will also experience London dispersion. But the strongest force it will experience is hydrogen bonding. It actually will experience all 3. But the question is, which one is the strongest? Hydrogen bonding. Okay, E was CH3Cl. Gotta hurry. So what you should have for that is you should have a carbon and 3 hydrogens. We know none of these hydrogens are polar or polarized. And then we have a chlorine. Okay, so we do not have hydrogen bonding here because we do not have a lone pair on an oxygen, nitrogen, or fluorine. And we have no positively polarized hydrogens. So the next question is this molecule polar? Will it experience dipole? And most people said that it would. So it must be, if we look at the electronegativity chart here, chlorine is 3.0, carbon is 2.5. That is a difference of 0.5. That is polar. And that is classified as a polar bond. So this bond right here between carbon and chlorine is polar. So we could draw in the partial negative and the partial positive. We could draw in a dipole pointing towards chlorine. And the strongest force at play here will be dipole, dipole. This molecule will also experience London dispersion forces, but the strongest force will be dipole, dipole. Okay, last one. We're on the last minute, I know. F, I'm hurrying. CH3COOH. How do you draw this out? CH3COOH. You cannot draw it like this. You cannot draw this. Why can you not draw this? Because this carbon only has 2 bonds right here, okay? So we can't draw it that way, so let's redraw it the correct way. What we have to do is double bond this oxygen, and then we have an OH group, okay? And when you look, any lone pair on an oxygen, nitrogen, or fluorine, we said was an acceptor. Look, we got 4 of these things. I'm going to abbreviate A for acceptor. Okay, these are all acceptors. And we have this hydrogen right here. It is connected to an oxygen. So this is a positively polarized hydrogen. So because you have both requirements, a donor and an acceptor, this can hydrogen bond. That's the strongest force. It's also polar. It will also experience London dispersion forces, all three, but the strongest is hydrogen bonding. And most people picked hydrogen bonding for that last one. All right, that's it for today. I can reshare my screen if anybody was still writing, just let me know. But if anybody has any questions, I'll stick around. If you have any questions off of the homework for chapter 7, I'm happy to answer those. I know chapter 7 is really, really hard. So I totally agree. That was the toughest homework you guys have had. But don't give up. Don't be discouraged. If you have one bad homework grade, that doesn't tank that doesn't tank the semester. But also don't leave your questions unanswered on those. I will send an email with all